Hello, my name is Jonathan Lennartz from the University of Bonn, and I'm presenting our work on active learning for Scribble-based diffusion MRI segmentation, a collaborative effort between me, Golo, Pohl, and Professor Schultz, and part of the Unsure workshop at MICAI 2024. The segmentation of medical images, which are often three-dimensional, is a quite time-consuming task. A common approach to streamline this is using Scribbles, which are weak annotations that mark key regions of interest, along with some kind of prediction model that then fill the remainder of the volume. This process typically requires some kind of iterative refinement to achieve accurate segmentation, making the speed of inference and the convergence to a proper result quite crucial. The complexity of diffusion MRI data adds further challenges due to its high dimensionality, often involving literally hundreds of input channels. Previous work by my colleagues tackled this by using unsupervised representation learning to handle this large data size. They combined this with a random forest classifier that can be retrained quickly enough on new scribbles to provide interactive feedback to a human annotator, making this process quite fast and responsive. Building on this existing framework, we introduced several improvements. The most significant is the addition of an active learning component, which guides the annotator by suggesting where new scribbles should be placed. This is driven by uncertainty quantification through test time augmentation or simply TTA. Interestingly, we found that TTA alone boosts segmentation accuracy as well, simply by averaging the predictions that we get by forwarding the different samples from the TTA. On top of that, we've implemented anomaly detection using isolation forests, which help reduce false positives that occur when generalizing from sparse scribbles. Specifically in background regions, we found this to be quite helpful. For our experiments, we used the Human Connectome project dataset, which provides high-resolution diffusion MRI images. From this, we selected 93 subjects, focusing on two distinct segmentation tasks. One involving wide meta tracts of varying sizes, and the other focusing on structures that are found in the left and right hemisphere. We assessed the general improvements made by test time augmentation and false positive elimination. This is our anomaly detection approach on a set of initial scribbles and found them to be beneficial, especially in combination. Marked here as the red boxes. After generating the initial annotation and making predictions with a random forest classifier, we conducted multiple rounds of refinement, each time adding scribbles to one slice per class, following different selection strategies. The figure here summarizes how segmentation accuracy improves as more scribbles are added. Vanilla and random sampling served as baselines, where random sampling used TTA and false positive elimination, while vanilla did not. You can see that the changes aimed at general improvement from that you also saw on the last slide remain relevant throughout the refinement cycles. We also included a reference method that uses error sampling from true error maps. While these maps aren't available in a typical active learning scenario, they provide insight into a potential performance on an ideal uncertainty measure. As the graph shows, our entropy-weighted sampling significantly narrows the gap between random and error sampling, outperforming random sampling in almost all cases. Additional experiments on sampling strategies can be found in the paper. In summary, we introduced two key improvements to the diffusion MRI segmentation pipeline. First, we enhanced the automated inference with test time augmentation and false positive elimination. These strategies, quite straightforward improvements, significantly increase the segmentation accuracy from the initial scribbles, even before active learning begins. Second, we improved user guidance by incorporating uncertainty-based active learning. This method helps target the most uncertain areas, outperforming random sampling and making the annotation process more efficient. These advancements reduce the need for extensive human input while improving segmentation quality. Thank you for watching and see you at the poster session.